Hi everyone. Okay, so this is it's been about 3 months since I did the last video. So this will be an update video. I have to admit the machine, not much has changed on the machine except that it's been pretty much collecting dust for the last few months. But that doesn't mean I haven't been working on it. It's just that I've been working more on the electronics side of things. Reason is I was going to install the table, but before I installed the table, I wanted to make sure I have everything, you know, pretty much finished on the saddle. And one of the things I still had to do was think about the homing. So I can show you on Fusion what I did. It might be temporary, I don't know. Anyway, for now, I made this this bracket that moves in front of a proximity switch, and as you can see, it's slotted, so I can adjust a little bit here, and also I can adjust the proximity switch forward and backward. So this should be enough adjustment, I think. I'll have to thread some holes in the casting, but first I'll just put some double-sided tape, I think, just to make sure everything works before I drill and tap the holes. Okay, so of course a proximity switch, I don't know what's the repeatability of such a switch, but I'm pretty sure it's not within the tenth of thousands of distance. Anyway, so I started to look around for, I don't know, maybe very precise type of switches, and what I discovered is what you do is you use the proximity switch to find ballpark of where you want your homing, and then you keep moving past the proximity switch until you hit the index of the encoder of the servo motor. And this is very precise, but how to do it? So I looked around again, and I found on the forum again a little sorry, what's the word? A circuit, electronic circuit using a flip-flop, like a little chip like that, and what it does pretty much, basically is that within this chip, it's waiting for the signal of the switch, the proximity switch. Then it sort of flips a switch within the chip, and then it's waiting for the signal of the encoder to like flip another switch, let's say it like that. And once these two switches are in place, they stay in place, because the signal of the index of the encoder might be a very, very short signal, and maybe the controller might miss the signal, but the flip-flop, that little chip, is not going to miss the signal, and it's gonna keep the switch on even though it's past the signal of the index. So the signal stays on, and the controller will catch it next time around, which is very fast. So this should be very, very precise. So I had to to make that circuit, and I started this took me into the rabbit hole of I thought I'm going to have to make a motherboard of some sort, or breakout board or something. So might as well make start working on the motherboard and integrate this homing circuit within that board. and this is what took me into the more electronic side of things. And I'm not an electric engineer or anything like that, so it's a slower process for me, because I have to do a lot of reading, a lot of studying, and trying to understand all these data sheets that I read, and try to make the good choices here. I have a few friends that know a lot of about electronics, and they give me a good hand when I'm stuck, so that helped a lot. Anyway, so I'm going to show you around my motherboard design. I hope this is not going to bore you too much, but yeah. So let's have a look at it. So for those of you who didn't know, Fusion 360 has an electronic environment, and it's pretty good actually. It's quite great. I hardly know anything about electronics, and I managed to do something I think pretty cool, and this is pretty much because Fusion Electronics is, I think, relatively user-friendly. Autodesk bought Eagle. They acquired Eagle and integrated it within Fusion 360, and there's an integration between the electronics and the 3D. You can pass, you can move from 3D to, anyway, it's pretty mind-blowing. So let's have a quick look at my schematic. I splitted it into 8 pages, so this is the sort of the power symbols and what's to do with the power. This here is the controller of my CNC, which is the UC300 ETH 5LPT from CNC Drive. I can put the link down below. So back to this quickly. I just mapped each of its connectors. You'll see why a little bit later. This is an ESP32. I think I've talked about those before. I don't know. There really are great little microcontrollers. They're little boards. It has Bluetooth and Wi-Fi, and it has two different cores on it. It's quite fast, quite a fun little toy. All these IOs. Anyway, I use them a lot in my projects. They're very inexpensive, and I use them on the board so that I have I can do Modbus, and anyway, and they give me a few extra IOs as well. Anyway, so ESP32 here. This is RS485 chip, and this is actually for the Modbus, because I use the Modbus a lot on my control. And this here is the homing circuit. So what I do here is, because the drives, the servo drives I have, don't use the index of the encoder. But I will use it in my homing circuit. So what I do is I have connectors for the encoder, a connector for the encoder coming in, and I send it right back out to the drive, but I intercept the index signals, and these signals are differential pairs. I don't know if you know what a differential pair is, but quickly, basically, you take one signal and you split it into two. You have like a positive signal and a negative signal. So if there is a signal, it's going to go like this, see? and at the other end, if there was noise coming from AC power or whatever, the both signal will have been subjected to the same noise, so you can compare both signal at the end and subtract what's the noise from the real signal, so you can have wires that go through more noisy environment and get a good signal at the end anyway, even through pretty long wires. Anyway, so all the signals from the encoders are differential pairs. So I have this chip here which will get the differential signal and decode it into a single signal line. And this here is these chips I talked about, the flip-flops. There are 7474s. And yeah, so you have the limit switch that comes into this flip-flop, and also the encoder index that comes in, and you have that signal that comes out when both have been activated, and this is sent to that UC300 DTH control. Anyway, so that's basically it for the homing circuit, and I have these connectors that will go to my switch, my proximity switches for each axis. So this is the homing circuit. Over here I have the connectors that go to the drives, the 3 drives. And these drives have error lines and reset lines, and I've read the manuals a couple of times, and I think I understand, but I haven't quite decided yet how I'm going to use them. You can use the error line and the reset line separately, or you can connect them together, and the way, if you have an error, it's going to behave a little differently. So what I did is I just made some jumpers, and depending on where I put the jumper, I'll have access to both modes, if we can call it that way. So I'll try both and see what I like most. And anyway, so that's pretty much it for this. This is the drives. And over here it's various inputs and outputs, like spindle probe, the tool probe, spindle lube switch, to monitor the spindle, the spindle lube and the way lube. The doors, I'm going to have sensors on the doors, make sure they're open or closed when they have to be, whatever. Chiller temperature, air pressure, coolant level, and this port is for extra IOs that I haven't used on my controllers, the CNC control and also the ESP32. So I've mixed them in there. If I ever need more IOs for whatever reasons, I can plug into this. These are 2 DB25 connectors. One goes to the control of the CNC, where I have my MPG and a monitor and so on, and the other one goes to the spindle and the automatic tool changer, for all sorts of to monitor whatever all these proximity switches that tells you whether the tool changer is in what position and so on. So yeah, this connector is for that. And this here, I'm not sure yet, but I'd like to install an encoder on the spindle. I think I know how I'm going to do it. It shouldn't be too hard. So, thinking that I might do it, I installed a chip to encode the signal from the encoder as a differential pair. So yeah, that's why it's there. And this goes to a different PCB. So I have 3 PCBs. I have the motherboard, which is what we're looking at right now. I have a PCB for the control and a PCB where I'm going to, it's pretty much a breakout board where I'm going to split the signals with different connectors to whatever proximity switch or whatever. Okay, and last page is for the relay module. And I'm pretty sure many of you are not going to agree on this, but to start with anyway, I'm going to use these modules. There are 16 relays. They have all the optocouplers already there to protect the motherboard. And what's nice with them is that all the inputs for this board is 5 volts, so it's very easy to connect to the control. Anyway, it's like nice little package. It's very inexpensive. I can have a few spares of those, and if one breaks, I just unconnect it and connect the other one, and that's going to be it to start with. I'll have 2 of those on the machine, which gives me 32 relays, which is a little more than what I need. Okay, and now if we look at the circuit itself, this is what it looks like. It's the most complicated thing I've ever made in electronics. It's a bit hard to see what's what in here, so we'll look at the 3D model of this. So this is it. This is what the motherboard is going to look like. And if I match it with these relay boards, this is what it's going to look like. This here is the CNC control, what I call it, the UC300 ETH, whatever, 5LPT. Anyway, I'll have the link below. So this is the control for the CNC, and really what I'm going to have is just ribbon cables that go that connects the control to the motherboard. So the motherboard is really pretty much a breakout board with a few circuits on it. So, and same thing here, I'm just going to have these ribbon cables that go from the motherboard to the module, and same for the power here. Over here I have my ESP32 and the RS485 here. If we look below the control, you can see the chips for the flip-flops and a little more circuit. I can actually, if we look at the motherboard over here, and if I hide the packages, you can see how they're all arranged underneath. And the connectors, I have my homing switches that connect here. I have RS485 out here, which connects to the Modbus. My Wayloop pump, my spindle lube, my left door, right door, air pressure, chiller temp, coolant level, my power on. This actually will control the how the computer and the control how everything is going to power down and power off. I'm not quite sure yet, so I have connectors for both, but I think they're probably just going to be using one of them, probably literally the switch from the computer. Still have to work this out, not quite clear yet. Tool probe, spindle probe. So that's pretty much it, and these are the two connectors for the ATC and the spindle, and here the control. Here I have my encoder in, encoder out for each of the axes, and over here the connectors for the drive. These are all RG45 network cables. And over here the two jumpers, depending on which way I want to use the reset lines. So yeah, that's pretty much it. That's the motherboard. If you have any questions, I'll try to answer them, or even suggestions. Of course, I'm always open to suggestions. I even have this little QR code on the bottom of the motherboard, which will take me with my phone straight to my GitHub page, where I'm building slowly all the document pertaining to the electronics of the Fadal. Yeah, so that's pretty much it for the motherboard. So now we're going to look at the control. Okay, so control panel. I've got only one page. This is the whole circuit. There's an ESP32, a few chips. These are optocouplers, quad optocouplers. These are resistors, network resistors, and otherwise we have, the rest is pretty much all connectors. We have this big DB25 connector from the motherboard, and these connectors we have scale select, axis select, the buttons for the jug, feed override, spindle override, tool select, single line. Tool select is to choose which tool I want, switch anyway. Yeah, on the automatic tool changer. These are all buttons on the control. Single line is to work the G code in single line. This is to activate the optional stop. Turn on and turn off the lights in the machine, turn on, turn off the mist, because I want to try something with mist. It's pretty much actually air coming through the coolant nozzle, so I'm gonna try. We'll see how it goes. Coolant, of course. This is going to turn on and off the coolant. Spindle on off. Home the machine, reset the code and whatever. Emergency stop, that's the kill switch. EMPG, cycle hold, cycle start, power on, power off for the whole machine. Again, maybe this might turn out to be just one button. Still have to see. The tool probe, probing the tool. You push the button and hopefully this will probe the tool. Table front is just to take the, just save some jugging time. Push one button and the table will, in Y, will come all the way front, and whichever G work offset is selected, let's say G 54, then in X the table will take G54 0 in the center of the front of the machine. That's the idea. And turn on and off the chip auger, which I don't have yet. I still have to see if I can make one. Otherwise, yeah, that's pretty much it. What the ESP32 will do, it has to work with the scale select and the axis select. I need the ESP32 to decode the signal, whatever. Anyway, so these buttons need to go through the ESP32 pretty much. Also the feed override and the spindle override work with, and also the tool select. These three buttons are encoders with the switch, and they also need to go through the ESP32, and then they're read through Modbus by the control. Anyway. And otherwise, what the ESP32 does is switch LEDs on and off on the buttons, on certain buttons, and that's what the optocouplers are there for. Is just because the ESP32 sends 3.3 volt signals, and the LEDs on the buttons are 5 volt. So I use the optocouplers to switch anyway on and off the signal so that the LEDs get enough power. Anyway, so yeah, that's pretty much it for the schematic of the control, and oh yeah, there is also this RS 485 chip that for the Modbus, again, to connect the ESP32 to the Modbus on the motherboard. The PCB itself, that's the 2D PCB. If I hide the polygons, this is what the circuit looks like. Again, it's pretty hard to show what's what in here, so we'll move straight to the 3D PCB. So that's what the 3D PCB looks like. Again, it's pretty much a breakout board, a connector for each of the buttons on the control, and this is what the control is going to look like, I think, so far. I have this very nice little touch monitor, so I can access any of the controls on the monitor. Even there is a pop-up keyboard, so I don't need a keyboard, I don't need a mouse. I'm going to be able to do everything on that little monitor, and it works really quite well. I experimented a bit with it, and I think I'm going to like it. But still, I wanted to have some physical buttons under control. So of course on the MPG, and I'm going to use the original MPG from the Fadal. These are my axis and scale select buttons. The tool select, the spindle override, and the feed override are pretty cool. They're actually little encoders. I'm gonna just turn off the back cover quickly. There are these little encoders, so you can turn them. They're not like a potentiometer. You can turn them indefinitely, and when I turn, let's say, the feed override, this is going to change over here. Right now it's at 100%, so if I turn it down, it's going to go 90, 80, 70, 60, and so on, and turn it up, it's going to go into a 10% increment. And if I push on it, it goes back to 100%. So that single button can do quite a lot. And I have visual feedback here on the monitor. Same thing for the spindle. And the tool changer, I think, is going to be good fun. This here is the actual tool. And when I turn the tool select, it's going to increment one by one, positively or negatively, of course. So if I'm at tool 15 and I want to go to tool 17, I go click, and I'm going to have the visual feedback here that I am at 17, and I just push on the button, and this will tell the tool changer to change the tool to tool 17. So I think this is going to be very efficient. And also I can do it on the screen. Everything can be done on the screen, but I think some physical buttons are going to be much better. And these buttons here have LED rings in them. But the LEDs are not controlled by the button physically. It's the control will tell the LED to be on or off. So maybe, like, let's say the coolant, I can turn it on and off with the button, but the G code, of course, can turn it on and off. So the LED will reflect whether the coolant is on or off, not whether the button has been clicked. These are all momentary buttons. So momentary buttons, I think. Yeah, I think this is going to be pretty nice. Just at a glance, I'm gonna know what is on or what is off. Or the reset button will be pretty much, I think, the same as this button, which can, flash red if something is wrong. So I think this button will be red, but otherwise they're all going to be white. And since I'm driving them with the ESP32, I'll be able to do some pulse width modulation and dim them higher or lower. So maybe I was thinking maybe have them fully on, as a to show whether it's on or off, but maybe the off state might not be completely off, but dimmed out, so that when it's working lights out, I can still see the buttons. Anyway, so that has to be seen. So again, I have the emergency stop here, the kill switch, right in the middle, easy reach. I have power on, power off, and the reset and the home machine. These all going to be used pretty much when I power on the machine. So I thought I'd keep them close together. Tool select and probe tool. So let's say I'm probing all my tools. I can go next tool, click, and then probe. Next tool, click, probe. So that should be pretty cool. Homing the machine, just homing all the 3 axes. Spindle override, spindle on off, and I'm thinking probably spindle on, spindle off, and if I push and keep the button pressed for, let's say, 3 seconds, then the spindle could start counterclockwise. Yeah, it might be fun, I don't know. But since I'm very rarely using spindle counterclockwise, I might just do it over here on the monitor if I ever need to. We'll see. Coolant on off, mist on off, chip auger on off. I want a chip auger. At work I have one machine which has a chip auger and one that doesn't, and I mean, it's such a big difference to have the chip auger, the chips to be thrown out. And even I'd like to have like coolant that clean, that flushes both walls and floors of the CNC whenever I need to, like curtains of coolant. I'd like to have that too, so that the cleaning is more easy, quickly done. Anyway, so chip auger, feed override, optional stop, single line, the lights on the machine, and 2 USB ports. So that's it. That's pretty much the control. If we look on the back, we can see where the PCB is going to be. This is the connector from that comes from the motherboard, or goes to the motherboard. This is 12 volts for the monitor, which connects right over here. That's the little monitor seen from the back. And each of these connectors connects straight to whichever of these switches or buttons or the MPG or whatever. They're all there. Modbus over here. And these are the optocouplers and the resistors. So yeah, that's pretty much the control. I've started to work on the pivot of the control, but I'm not finished yet. I have this slot here because DB25 connectors are pretty long, and I think I'm not sure they're gonna go through this small of a hole. So anyway, we'll see. To start with, it's going to be a 3D printed part, and as soon as the machine is making chips, I'll make it out of brass or something like that. Okay, so that's it for the control panel. Now we're going to look at that little PCB for the spindle and the ATC. Okay, so now the ATC and spindle schematic. Again, we have the DB25 connector that comes from the motherboard. We have this chip that encodes, that takes the both signal from the spindle encoder, if I ever install it, and split it into differential pairs. So that's what that chip is for. And we have a series of connectors that monitor each and every limit switches in the spindle, like the drawbar and the tool changer and so on. I have the carousel aligned, which is its radial movement, carousel forward, and carousel at rest. Conflict, there is a limit switch within the tool changer. If let's say the spindle already has a tool in it and it's trying to place it on top of another tool, that would be the worst case scenario. This will push on the carousel, put a pressure on it, and there is a bunch of Belleville springs and a limit switch, and mechanically it's pretty well done actually. And if there is pressure put onto the carousel, that limit switch will trigger, and everything will stop. This is my job to make sure that everything stops in my program. But yeah, so this is what's that conflict connector is. Otherwise, manual tool release. Okay, this is one thing I want to do, is have a button on the front of the head of the machine to release the tool. There is one on the Haas machine, and I think it's way more practical than have your arm all extended on the control, and like that. I don't think it's a very good idea to have the tool release on the control. I think it's much better in the machine. So I want to have that. I'm going to try to find a way. The spindle encoder, we talked about that. The belt tensioners. The Fadal has two different belt arrangement for the spindle to faster or slower. Anyway, so these are they have proximity switches on them to confirm their position. So that's what these are. Spindle orient. You have to orient the spindle before you change tools. So that's what this is. And the drawbar open. Yeah, so that's pretty much it for that. So it's a very simple PCB. That's the PCB here, the DB25, little capacitor here for the power, and the different connectors. So that's pretty much it. And if we look at it, that's what it looks like. I'm not sure where it's going to be in the machine, somewhere in the, a control box somewhere. I might make it a little enclosure to keep everything clean. But yeah, that's pretty much it. Very simple. Maybe I tried to split them, like everything that goes to the encoder, the tool changer, and everything that goes to the spindle. I tried to separate them a little bit, so I might have to tie wrap them all together or something. I don't know. We'll have to see. This might change. I mean, this is just it's not a big deal to modify it later on. So I'm where I'm at right now, and we'll see. Something I'd like just for fun to show you. I use a lot just to show you Fusion Electronics just quickly, because I think it's pretty awesome and I'd like to show it to you. So we have these polygon pores. Show all polygon fills. So these basically are copper. All that's red is copper, and you see you have the traces isolated from the copper. So all copper parts are kept into one big thingy there. So you see all these are copper, so they're just filled. Yeah, so first thing I'll do is remove these because I'm going to show you the auto route feature of Fusion. It's pretty awesome. What I do is to have like thicker traces and thinner traces. I have made like a they call them net classes. That's right. So I have different net classes, one for power where I want thicker traces and the default and whatever, and I can just into this in settings somewhere in the DRC rules, whatever. I set all this up. It's not that hard, and you have all these different layers where you can tell auto route not to go like over these circles here. Just tell Fusion not to auto route in this area. All the traces that are blue are on the bottom side of the PCB, and all the traces that are red are on the top side. You can have up to 16 layers like that. This one is going to have only 2 layers. So I'm going to rip up all of the traces. Yes. And as you can see here, I have a few traces that did not rip up. This is because I locked them. I didn't want them to I routed them manually, and I wanted them to stay like that, so I simply locked them. These here are differential pairs, and they've been tuned so that both of them have pretty much the same length. So yeah, that's it for now I'm ready for auto routing, and you'll see it's pretty fast. I'll just click that button. I'm having the top and the bottom layers automatically routed. Next, and now ready to start auto routing. Check this out, it's quite fast. Takes a few minutes. There you go, it started. How awesome is that? That's it, done. Thank you. Auto routed. And then I can pour my polygon fills, one for the top layer. This is for ground, and one for the bottom layer. Ground. There you go, and then I press here to generate the 3D PCB. It's already it already exists, but it's, you know, redoing it with the new traces arrangement. So there you go. It's quite awesome, isn't it? So yeah, that's it. That'll be it for now. It's a pretty long video, I think. I'm not sure how long it is, but long enough. Thank you for if you stuck with me all the way to the end. Thank you very much. Especially if you're not into electronics, then you're very courageous. And hopefully the next one will be testing the homing. I'm going to make a test circuit on the breadboard and try the flip-flops on the actual machine and make sure it all works before I go any further. Okay, thank you very much for watching, and I'll see you on the next one. Bye.